Hello class, welcome to our final lecture of the semester. Today we're going to talk a little bit more about quantum information, and next class will be used for answering questions, hopefully on Zoom if we can set up a good time. Hopefully the time that the class is actually scheduled for works out okay. And then next week you have your finals, and then you're free. Well, free from this class anyway. Okay, so today is lecture number 19, and we are going to talk about quantum teleportation. All right. Sort of a buzzword that crops up every now and again in when people talk about quantum physics in the popular media. So today we're going to learn exactly what this is. What is quantum teleportation? It's very likely not what you think it is. So before I start talking about that, I want to talk a little bit about what's called the no cloning theorem. So the no cloning theorem is pretty simple. It just states that you can't copy quantum information. Right? This is pretty strange, because if you think, well, if I have some classical information, if I have a page, or, page of numbers or a page of text or something like that, I can just sit there and I can just copy what it says on the page. But if we have a quantum state, say we have some state, and it has a 50% chance to be spin up, or a 50% chance to be spin down, well, all right, I shouldn't use Brockett notation. You guys don't know Brockett notation. I'll just tell you what this is real quick. So this is, when I write the line and the caret like this, this is a representation of a quantum state. When you get to your real quantum class, you'll learn all about Brockett notation and what these things mean. That's a way of writing quantum states as a vector. I don't have it in the rest of the lecture, but just for demonstration, I'll just write it here. Okay, so if we have some quantum state, say we have a half chance that this particle, whatever it is spin up, and half chance that it's spin down, that proportion of how likely it is to spin up and how likely it is to spin down is lost when we measure this state, right? If I give you an unknown quantum state and I say, what is it? The only thing you can really do is measure it, and then you get a result. You get spin up or spin down. You've lost the information about the relative balance between its chances to be spin up or its chances to be spin down. You only know that you got that one result. So that full information about what the state looks like is actually lost, all right? So when we observe a quantum state, a consequence of the observer effect, a consequence of the measurement problem, is that when we measure a quantum state, we lose the information about it, okay? So the no cloning theorem just states that we cannot copy quantum information. And this is the reason that take a sip of tea. That's the reason that quantum key distribution protocol that we talked about last class, that's the reason it works, right? If Eve could just make an exact copy of any quantum state that was coming, if Eve made a copy of any quantum state that was coming her way, and she could do that, well then she could, take out of the stream of information some particle, measure its quantum state, make a copy, send that copy to Bob, and then she could disguise her presence that way. But because she can't do that, the protocol works. All right? So, how much information is stored in the quantum state before measurement? Well, that's something that's sort of interesting to talk about, and it's a bit subtle, right? So there is a way of conceiving of quantum states using what's called the Bloch sphere. This is the Bloch sphere. It's named after some guy named Bloch, B-L-O-C-H. There are several physicists named Bloch. I forget which one the sphere is named after. But, so suppose we have some quantum state, it's unknown, psi of u equals alpha psi up plus beta down. Okay? We represent this unknown state with some variable in front of each of these basis states. We can represent each of these by a point on this block sphere, right? What we usually do is we draw a vector pointing to a point, and if this vector points to the North Pole, well, we'll call that, we'll call that, let me erase this. This is our psi up, all right? So this would mean that alpha is equal to 1, and that state is definitely just in that state there, okay? And then, if we wanted psi down, that would just be this guy down here. Okay? So, if we take the relative proportion of alpha and beta, right, we don't necessarily just have alpha equals 1, beta equals 0, beta equals 1, alpha equals 0. We can have any weight between these two, including negative values, and that any real number weight between these two constants sitting out front is another state pointing on this great circle on our block sphere. So this one, for example, there, that would be that state I wrote the first time, 50% up, 50% down. And now we're more weighted towards beta. And then we can even go in the other direction, right? Because these can have minus signs in front of them. When we take the probability of finding this particle in one of these states, we take the modulus squared. So these numbers are allowed to be negative, so we can also have numbers around here, right? This state would represent that same state we have over here, but with a minus sign, and et cetera, all the way around this great circle. And we have this length of this vector is uniform, right? Because the magnitude of this state, right, is always essentially 1, right? Because we have to normalize that state to probability 1. It's going to be in one of these states. Okay? What about this other direction? Well, in this direction, we realize the imaginary possibilities for alpha and beta, right? Because we take the modulus squared to get the probabilities from the probability amplitudes, we're also allowed to have alpha and beta take complex values, and those are represented, right? So this would be psi up plus psi down with some relative imaginary phase between them. So this would be psi up plus I psi down, right? With that root 2, 1 over root 2 factor in front. And the same all the way around here. So what this shows you is that this quantum state can be represented by a vector that points to any point on this sphere. So if we could read the quantum state, if we could see what it is, we could actually encode essentially an infinite amount of information in it, right? Each one of these points is a different, distinct quantum state. But of course, we're limited by our ability to measure, so we would say not that we have an infinite amount of information here, but just a lot of information, right? Because perhaps we don't have measuring devices that are good enough to tell the difference between those two states, right? Even in principle. So we have, in principle, a large amount of information that we can put into a quantum state, but when we measure it, we get one result, and we erase all of that information, right? Except for the answer that we did indeed get one particular state out. So that state has to be among the possibilities. Okay. So entangled states are sort of like two vectors for two particles. If we have a state, well, I'll just write the state. If we have a state that looks like this, psi equals, let's say psi AB equals psi A up, psi B down, plus psi A down, psi B up. Okay, we could represent this by saying you have possibility that A is up, right, and B is down, or that A is down and B is up. I just want to point out, I don't know whether this is useful to know or not, but this is what's called a maximally entangled state, right? I could have a state that's not as entangled, that didn't have these vectors perpendicular to each other. They could be closer. Also, they could be a mixed state, which you won't get to that till your advanced quantum class, right? That's the state that's not entirely quantum or entirely classical. It's somewhere in between. So these states that have this property that they're maximally entangled, that they're opposite, they end up with opposite projections on the Bloch sphere, are quite useful for quantum technologies. Okay. All right. So there is a class, or rather a set, of maximally entangled states called the Bell states. It's named after a person, John Bell, who's the same guy that came up with the Bell test, or the Bell inequality that we talked about last class in Wigner's interpretation. He also lends his name to these states. So we have 4 Bell states. I will write them. Next one I'll have to save some space. So what these are, I'll talk while I'm writing the last one, is a set of maximally entangled states for 2 spin particles. Right? And like we can write one state in terms of some other states, right? We can write some weird wiggly quantum wave function that looks like this in terms of sines and cosines, right? If we add them up all in superposition, we can write some state as a combination of states like this quantum state or a Fourier transform. Because we can do this, we can also write quantum states in terms of other things, right? That choice of decomposing a wave function into sines or cosines, that's one choice of a basis. We could also decompose it in terms of other functions, right? For example, the polynomials that we get from solving the hydrogen atom, that's another complete set. We can write some quantum wave function in terms of other wave functions, right? So this series of Bell states gives us a complete set that we can write any 2-particle spin state by adding up these 4 states, right? So let's look at these 4 states. It's psi minus, psi plus, phi minus, and phi plus. right? And they're all equal weighted between spin up, spin down, minus spin up, spin down. And then phi plus is that same thing, but with a plus here. Phi, instead of having up, down, down, up, we have up, up, down, down. And then minus, minus, plus, plus. And then this again, this phi is up, up, down, down. Okay, so any two particle state we can write by adding or subtracting however many of these states we need to, right? So that's a bit of background. Now, these states can be used to violate a Bell inequality, like we saw last class with those Wigner inequalities, right? We didn't say how we would violate that inequality in a physical system, but the way we would do that is we would find some physical implementation of one of these states, and each of these states can then violate a Bell inequality. Why they're part of why they're called Bell states, right? Okay, so now we know that we can't copy quantum information, right? We can't, get a quantum letter, make a copy of it, and send that to somebody else. But what we can do is teleport that information. And when we teleport that information, when we teleport a quantum state, the point of it is that we'll have our quantum state, right? The one that we want to start with, and we want to give it to somebody else, right? So what teleportation does is it destroys the quantum state that we have, and another person distant from us can recover that quantum state, right? That state is teleported from our system to the other person's system. Now, it's really important to point out that, we'll see this as we go through the protocol and how it works, but we're not moving anything physically. We're not transferring any energy or matter. What we're transferring is information, right? We'll see as the protocol works that what we need to do is be able to talk to the other person, send them information, and tell them what kind of measurements to make and what to do, and then they, in their system, recover the same quantum state that we had, right? They don't have the same physical particles that we do, right? They have their own particles, but those particles take on the quantum state that we have locally destroyed. So we can't copy quantum information, but we can teleport it, we can transport it from place to place by performing some clever tricks. Okay, so I'm just going to draw a diagram of what that'll look like. So classical copying, right, we have some unknown states, right, and we just make two of them. All right, quantum mechanically, of course, we cannot do this, but we can do something a little more complicated. So we're going to create an entangled pair. We're going to create one of those Bell states that we had on the previous page. So we have two entangled particles. This is how cool people write entangling on this little loopy thing. So we create some entangled state, right? That could be one of the ways we talked about last time. In principle, this could be something like a decaying pion that turns into an electron or positron. It could be a photon that gets split into two photons that always have opposite polarizations, or opposite polarizations. So this is our Bell state. Okay. And then one person has that unknown quantum state. And what they do is they take that quantum state, mix it with 1/2 of this Bell state and measure it, and then that person sends a classical communication to a distant party, and what happens is they take this entangled state, perform some operation given by this classical communication channel, and then they can recover that same unknown quantum state, right? So this isn't like we sent the quantum state. This thing never goes over here. It goes up here, and that quantum state is destroyed by the measurement. And then based on the results of that measurement, we're going to tell this person over here that has this half of the Bell state what to do, and they'll be able to get that quantum state. Now, this whole time, neither of these people need to know what this state was. Okay? They can teleport an unknown quantum state. Okay. So how does this work? We have some unknown quantum states. So this is C, the subscript indicates the person, right? The party A, B, and C. There's three parties involved, right? There's the party that has the unknown quantum state, there's the party that produces the entangled state, and then there's the person that does the measurement and receives the teleported state. So this is the unknown state to be, state to be teleported. And yes, I see. Yeah. Okay. So, I mean, you can do this in any basis or any system. I'm just choosing spin up and spin down because it's familiar. And in this example, alpha and beta are unknown complex numbers. They contain the information about what state this actually is. We'll also have an entangled state, phi plus Bell. And I will rewrite that. 1 over root 2, psi A, up, psi B, down, plus psi A, up, psi B, down. Okay. Sorry, I squeezed it in a little bit there, but this is up, down, plus, oh no, it should be up, down, plus. Yeah, down. Sorry. So it's psi A up, psi B down, psi A down, psi B up. Okay. So the first party wants to transmit or teleport this unknown state to the other party. So what the person who wants to perform the teleportation does is they hold on to this state, and they hold on to this state, they create this state here, and then she keeps half of this state, say particle A, and then sends particle B, the other half of the state, to the other person. So if we're saying Alice is the one who's transmitting the information or teleporting the state, Alice is essentially the first and second party. She gets the unknown quantum state from wherever, and she creates this Bell state, and she keeps the A part of the Bell state, and she sends the B part of the Bell state to Bob. So then the total state of the whole system is given by psi of u, this unknown bit, times phi Bell plus. Each party gets part of the state, right? This is the Bell state, and this is the unknown state. So actually, I'm going to write this phi plus AB, right, because it's shared between A and B. Even though I physically send the particle over there, we still share that state because that state is still entangled, right? No matter how far apart I move those particles, they still share the same state until I measure them. So now what we're going to do is we're going to invert the Bell state, which I wrote on the previous page, and we're going to write this state here in terms of those inverted Bell states. So we're going to do what I was talking about on the previous board. We're going to use that Bell states, that set of 4 Bell states as a basis to write any quantum state. We're going to use it to write this quantum state. So by inverting the equations I had on the previous page, I get psi up, just a regular state, unentangled with 2 particles pointing up. Okay? Just no quantum weirdness going on. Though this is a quantum state, it's just 2 particles pointing up, and definitely 2 particles pointing up. But I can write this this normal seeming state in terms of the Bell states. So I can write this as 1 over root 2 phi plus phi minus. I'm not going to write the Bell subscripts. These are all Bell subscripts. And then psi down up. This is 1 over root 2 phi plus minus phi minus. Be careful with my phi's and psi's. And then we have a state where first particle's up, second particle's down equals 1 over root 2 phi plus phi minus. And then we have phi, or psi, excuse me, down equals 1 over root 2 phi plus minus psi minus. Okay, so we're writing unentangled or separable states in terms of this entangled Bell basis. Okay. So I'm going to erase everything, so prepare. So now the total state, right, that psi u times psi AB, I can write as 1 over 2. This is a long equation, so I will write it and then I will explain it. You know what, this is a lot of writing, there's no reason for you to watch it. Okay, so I wrote everything out. So this is that same state we had before, except now we're writing everything in terms of these Bell states, and you can see that we still have this psi b, right? That contains, or excuse me, this, not psi b, but this whole thing in brackets in front of each Bell state, right? This is where that information is, right? I still have that alpha in front of b, I have beta in front of psi beta. So I've rewritten this state in terms of these 4 Bell states, right? And then the unknown information is in this psi b. Okay. So So the magic that's happened is that originally that, not really magic, it's just simple algebra. But by the way, you can check this. I mean, you can plug in the Bell states and plug through and see we get what was on the other board. But the magic of this is that this alpha and beta, right, they're not in front of psi c anymore, which is what they originally in front of. They're now in front of these psi b's. And that C is now part of this state, this Bell state that gets multiplied out. Right? That's just algebra essentially, and you could see that if you plugged in the Bell states and went through this, you could see we get back to the other thing before. Okay, so what we've done is change the basis we're looking in. So this is a bit like rotating that block sphere. So imagine, we've got, actually 3 block spheres, 1 for each quantum state. Each there's vectors on them. So what we're doing is not moving any of those vectors around. It's like we're grabbing the sphere itself and changing our definitions of what states are. So we're rotating those block spheres to change our definitions, and we're changing that so that this is all now in a new basis. So we haven't done anything physically to the system. Nothing's changed. We're just changing the way we mathematically represent it. So each term of this expression is a superposition uniquely associated with one of the four Bell states. Right? And as I was saying, the Bell states are now written in terms of A and C instead of A and B. So the next step is that Alice, right, performs that measurement. I'll draw the diagram again. Alice performs that measurement on the Bell state. So now the unknown state I'm calling psi c because that's how we had it defined before.